Hello everyone. We are here recording video and recording audio for a kind of new format maybe for Nimiq, which is supposed to be a slightly more technical and more open-ended discussion about specific topics together with some experts on our team. So today I have Pascal, which we all know and love, and we have Bruno, which is a new addition to the team.
True.
And we will today talk about what they are working on for Nimiq and for Albatross, and also introduce Bruno. And I think we're just going to start with that. So, hello Bruno.
Hello.
Welcome from everybody to the Nimiq team. We're very glad to have you.
Yeah.
And I hear you are working on Albatross.
Yes, I'm working on Albatross now. More on the theoretical design part of the protocol, because I'm not actually a programmer, I'm a mathematician.
All right, okay.
So yeah, it's not my strong suit, programming, but yeah, I'm working with Pascal and the rest of the core team on Albatross.
Nice, so you studied mathematics?
Actually, I studied physics.
Physics,
but
okay.
it's quite similar. Yeah,
Yeah, it is. It's lots of mathematics.
Yeah.
Okay.
Also, then later I started to get more into applied mathematics, so cryptography and
All right.
A bit of machine learning also. And so that's how I end up a bit interested in blockchain. Actually.
Yeah, that's what actually exactly where I was going. So you learn about blockchain at some point and then found it interesting, or how did it go?
Well, the first time I heard about blockchain, it was actually a long time ago. It was around 2011 or something. There was only Bitcoin and Ripple at the time.
Ripple, okay.
Yes, the first two ones actually at the same time. And at the time it was not even called cryptocurrencies, we were more about the new monetary system and all very crypto anarchists or crypto punk, feel to it. But yeah, I saw it at the time and I became interested, but still more as a theoretical concept, because there was really nothing at the time. Could buy it in Mt. Gox, I guess. It was the only place.
Oh, Mt. Gox, yeah.
It was worth pennies, so I just forgot about it for a lot of years. Then I became again interested in 2014, I think.
It's really interesting for me that you still know like the years.
I know because I keep like an online resume, so
okay.
the only way I know it actually. No, actually the first date I'm not sure, 2011. The other I know because it was 2014 and it was actually my first paper on anything related to blockchain. That was actually on anonymity on blockchain.
Right.
It was a series of two papers on that.
Was it the one on the mini blockchain scheme?
Exactly.
Yeah.
Some homomorphic mini blockchain
exactly.
scheme, I think. Yeah. And yeah, then again, I also forgot about it for another couple of years because nothing really happened.
Yeah.
Way later, in 2018, I guess, out of nowhere, because I was not interested in blockchain anymore. I was going into
when Nimiq was already taking off.
Exactly, you were. Then I got like 2 emails from 2 different companies that read my 2 papers from several years ago, and they wanted me as an advisor. And well, now we're here, basically.
Yeah.
So yeah.
And then you started work on the Albatross white paper, and now
quite a lot later, yes.
Quite a lot later, actually.
Yeah, quite a few months later.
But Nimiq kind of worked with the company you were at the time.
True.
Right,
yeah.
and so you got to know each other.
For the collaboration, yes.
Collaborated and developed a new consensus protocol. Sorry, so we had Nimiq 1.0 in JavaScript, written in JavaScript, and then the core team, you wrote the Rust version of the Nimiq 1.0 or 1.x protocol, proof of stake version, and then you started adapting that to Albatross. Why did you choose Rust though?
Okay, sure. So basically for the same reasons why we chose to implement the first version of Nimiq in Rust as well. The obvious benefits of Rust over the JavaScript version are basically the speed. It's much faster than JavaScript implementation. Also the memory footprint is way smaller, which is very good. And from a programmer's perspective, or also bug catching perspective, basically. Rust is a typed language and has a lot of memory safety features, so it's much easier to catch bugs up front compared to something dynamically typed like JavaScript. And yeah, that's basically why we implemented our whole blockchain protocol in Rust in the first place. And then it was more about the decision whether we want to basically implement the new protocol in JavaScript first and move it to Rust afterwards. But
okay, so it was pretty clear already that it needs to be in Rust anyway to be efficient.
True, exactly.
So you didn't need to go the extra step to go to JavaScript first and then transpile it now. Okay.
Exactly. And since we wanted to transition basically to the Rust version anyway, that made more sense. And one other benefit of Rust basically is that it can be compiled to WebAssembly, which is very important for us because we want it to run in the browser.
Yeah, we still want to be browser first, or be able to run it in the browser and connect directly natively to the network, to the peers.
Exactly.
Cool. So when you started working on the implementation of the white paper strategies and the white paper ideas, did it all work out? Could you just simply take a chapter of the white paper and say, okay, now I'm going to put this into code?
I mean, that was the idea when writing the white paper. Of course, when actually starting to implement stuff, you realize that parts are basically maybe too high level, there's information missing or ambiguous, and so a few things happened since then. Also, we improved the Albatross protocol, the first version of the white paper. Since then, basically.
There's been an iteration.
Yeah, there has been
white paper with new sections and new details. Could you give an example of which part you had to revise? Also, after you detected that it didn't quite work or was too high level.
Yeah, for the too high level part, maybe one example, it was basically the PBFT. True, exactly. Because I mean, in the white paper, we basically wrote, yeah, it's PBFT, standard PBFT.
Because it is a known algorithm already.
So PBFT, that's the part where it's decided which nodes are honest and which parts are not honest, or
it's basically the voting portion of it.
Yeah. Okay.
In the macro block, when the nodes basically have to vote in 2 rounds and approve the macro block,
right.
The thing is, and basically the white paper said, I think I remember the sentence something like, we don't have to care about forks because PBFT is a forkless protocol.
True, yeah.
And so what happened after our first implementation and when actually running the first versions of the DevNet, we got forks in the macro blocks. So it shouldn't happen. The question is, what's wrong? Is PBFT broken? No, it's not. Yeah. It's just the specification was not detailed enough. Okay. And there are a few possibilities how to basically implement PBFT at that level. And we had to look at that again in more detail and decide actually for one of these possibilities. So and now it's forkless.
You kind of went back to, you didn't go back to the drawing board because you already knew we need PBFT and that's basically what it is. But
yes, we needed to get more detailed about it. I think it's the best way to describe it, because we knew we wanted PBFT for that section, and we also knew that it should work. It's just that there are a lot of small details that we need to get right, especially the timeout protocol portion of it. How nodes handle when other nodes just go offline or start behaving in a Byzantine manner, and that was not very specified in the paper. Again, because it is a known algorithm, but there are a lot of variants of it, and it actually is a tricky one to implement, more than we expected.
Yeah. Interesting. Yeah, cool. Okay. So, we already went there. So, what's the current state? Where are we at with development and with realizing the theory in code?
So right now, basically, the Albatross protocol itself, as described in the Albatross paper, has been implemented we made a few adjustments, basically going a step back again to your previous question.
Okay.
For example, we made some changes to the staking behavior as well. So what we did in a nutshell basically is that we simplified and so first of all we separated validators from stakers, and so we simplified the staking model a bit, and now it's very easy basically for people to stake or to delegate their stake to validators.
Right, so this was a big improvement, like, because when I hear you separated two things, then I don't necessarily think that's now easier, but it makes it easier to do either of the two, and because they have less dependency on each other.
Exactly. Yeah.
Okay.
And so that was a very practical problem that we had to tackle basically. And what else do we have?
So just quickly going, hooking into that. So that's the whole thing where now we can actually stake from I can stake from my personal wallet.
Yeah.
I can assign this stake to a validator that is registered in the network, which is a separate thing, registering as a validator.
Exactly.
And I can go offline because the validator is now working with my stake as well. And I can go offline. I can close my wallet and come back later and see that you hopefully paid out my rewards to me.
Yeah, exactly.
Right. So this
That's
is
how
a
it works.
delegated staking pool.
Yeah, just delegated.
It's basically a staking pool.
Yeah.
Okay. That's nice. Yeah. So coming back to the stage. Sorry.
Yeah.
So
first of all,
when you're saying you basically already implemented the Albatross white paper, that means you have the consensus algorithm.
The consensus algorithm, yeah,
so
exactly.
The whole part underneath that actually needs to function for the blockchain to function.
Yeah,
that's not the consensus algorithm, right? The syncing and the network.
Yeah, there's still some stuff missing.
Storage of the transactions and blocks in the node.
I mean,
and that's a totally different layer.
I mean,
we still have that from the previous version. We just want to improve it a bit to handle the transaction load that's going to happen now. Mostly.
Okay.
Exactly.
But so
one other thing that actually a quite big change to the very original version of the Albatross paper was also the slashing. In the very first version,
that was a
good
good
topic.
improvement.
In the very first version we still had the slashing in there, which basically makes sense when you think about it. If someone misbehaves, take away his stake basically. But then when I learned about proof of stake first, that was kind of a given, right? To be able to join the network and to validate the network and to earn rewards for it, to secure the network, you are putting your stake at risk, right? Yes.
Not at risk, but you are
putting it at risk.
Yeah.
You can lose your funds in
It's
most
security.
other POs and POS.
It's an incentive for you to be honest and to in the network terms, and to do the right thing for the network.
True.
Okay, so sorry, I didn't want to do that, but so you found a way to not have that, or
or basically we found out why it doesn't make sense in our current model.
Okay.
Yes. It was more that we didn't find a way to not need it. We just find out that we didn't need it already, because most POS algorithms that we're talking about, like the Ethereum one is going to be, they don't really have finality in macro blocks, so they can fork and just keep forking to infinity. And so in that case, you actually need some type of slashing to keep people, behaving. In our case, we do have the macro blocks that provide a specific finality and
the macro blocks.
Exactly.
Okay. Yeah.
So you can misbehave and do other things, but at that end, you're going to get caught, basically.
Okay, so the macro block is like a security gate. Every time a quality gate,
exactly,
and there's only ever one of each height, basically. That's what you're saying, right? There can't be a fork, there can't be two blocks that continue. There's only ever one, and the majority or 2/3 of the stake validator weighted by stake need to agree
On the
market block.
specific block, exactly.
And then it's actually final. Then all the transactions that happened before
became final. Yes.
final and can never be changed.
And that is actually key, because the fact that you can't have infinite forks means that we actually don't need to slash people. We just need a bit of incentive for them to behave rationally, and what we then prefer is just slash their rewards only and not their stake.
Okay.
And that is enough. You just, since you can't gain anything from forking, the tiniest of incentives is enough.
Okay. So yeah, it's slashing the. Richie is trying to say us something. Tell us something.
You can also talk to us.
Also, yes.
Yeah,
you can
You
also
mentioned
edit
before
it
that
out.
that there's a way of doing delegated proof of staking, right? But it is non-custodial.
Yes, it's non-custodial.
Yes.
You didn't mention that.
Very important detail.
Yes.
You're right. Yes.
Yes, you never are at risk of losing your funds. Also, because there are no slashing, it is literally impossible for you to lose your funds. You can just delegate them and take them out.
The funds are always associated with your address, so you always have control of them. The validator only gets basic control of the rewards and can.
Yes.
A malicious validator could keep the rewards, but I mean that's the same as in mining pools right now. So
And staking pools.
staking pools in most of them actually, yes.
Yeah, that's very cool.
Yeah.
Actually, yeah.
And one more reason, basically, very quickly for staking, for the slashing, why we don't need it. So if we would have the slashing, it's actually also an incentive for validators to split up their stake, because if you slash their whole stake, you just, instead of creating one validator with a lot of stake, you create hundreds of validators with very small stake, so you don't lose much. So in that case, it doesn't make a lot of sense to slash. That's another reason, basically.
So basically, so just for me to reiterate. So in regular slashing situation, or when the protocol has slashing, to reduce risk, validators would just distribute their stake into smaller, separate addresses, separate nodes maybe, and that would, first of all, it would increase the amount of storage that the contract kind of needs to store all the different validators, all the different validator addresses, and second of all, so at that point the slashing doesn't make as much sense anymore. That's what you're saying, right? So why have it at all?
Sure.
If there's such an easy way for people to game it anyway.
Plus, we basically found that it's not needed incentive-wise, because, as you said, because of the market blocks and slashing the rewards. Yeah.
Cool. Nice. Very nice. So yeah, we covered already the part about things learned along the way. Very nice.
Yeah. And now we can finally go to.
And now we can go to we just continue in the timeline. So that was the current state. So we are at a point, just to summarize, where the consensus protocol, which is only the level where it defines how nodes vote and communicate, and what they vote on and what they agree on, and then the rest of the team is working on the syncing of the transactions and the syncing of the blocks, which are now much faster. So I heard, and maybe there will be another video and another podcast about that part. So there were some technical challenges about syncing blocks much faster from multiple different peers, and syncing the transactions also with higher transactions throughput. And I think we will cover that in a future episode. So going into the timeline, now we are going into the future. So our roadmap says that we are planning to release Albatross and hard fork, which we'll get into later, this year still. And so what's missing? What do we have to do to make that a reality?
Okay, so.
And also maybe what are you, because I see you also working on your laptop hardly, and so there's apparently also some.
I'm actually doing some coding now, against my will.
So you're both you are still working on some theories and like research, what we still need, and you are working on the implementation of things, and now you too. So maybe you can just
so
tell us a little bit about what you're working on.
In short, basically, there are two major things that are still missing that we have to work on. One is the basically nano sync, or all these very, very light client syncs that happen in the browser. And that's what we're actually working on right now. So maybe Bruno can tell something about this in a minute.
Mm-hmm.
And the second thing that's basically missing is the browser portion of it, that we're actually able to compile it to WebAssembly and run it in the browser. And these are the large points on the roadmap, basically, that are missing before we can do a hard fork. Yeah. Plus, we also, of course,
small stuff.
We have basically also figured out roughly how we want to do the hard fork from technical point of view, but details.
I think we can talk about this also in a few minutes.
But okay, so let's maybe first talk a bit about the light client sync.
Which I'm very interested in.
It's a very nice and cool part,
what front-end team needs to build into their wallet and to start integrating it.
The idea is actually very similar to what you guys had before in Nimiq 1.0.
Sorry, just very quickly, a bit of background. So for proof of work, there's been established research. There's been established methods for a longer time to have small proofs and to have a provable state in a very mini client in the browser. Right, that works for proof of stake, proof of work.
Yes.
But for proof of stake, this doesn't really exist yet, or there's been ongoing stuff. There's nothing stable yet. So now actually, we need to figure out how to do that, right?
Yes, for proof of work, there was a non-interactive proof of work, so the NIPOPOS, I guess it's normally the short name that you guys were using, and yes, it is a lot easier to do that on proof of work.
Okay.
Because the only information really that you need to condense is the nonce, is the difficulty in there.
Okay.
So there's not a lot of information that you need to condense in there.
Okay.
Nonce is 64 bits, I guess.
Yeah, I think so.
Okay, so yes, you have only a few bits of information to compress per header. Now, proof of stake, and especially our protocol, Albatross, it's a bit harder because
what? Sorry?
It's a bit harder.
A bit harder. Okay.
Yes, because it's header.
I kind of understood it's retarded, but I was like, what? No, that can't be.
It's not.
No.
Okay, yeah, it's a bit harder. Sorry.
Yes, it's harder because you don't have any difficulty or anything like that. What you actually need to prove is the signatures, the 2 runs of signatures of all the validators.
Yes, I can imagine. Yeah.
Exactly. And so each header we need to prove that all these validators that are like 512 now, maybe even more in mainnet.
All the slots per...
Exactly.
Per
they actually sign that header and they did sign it twice, and the signatures correspond to the public keys.
Right, so all this data would have to be shared.
There's a lot more information that needs to be compressed in there.
To be able to prove that the blocks actually happened in the order they did and that they are all valid.
Exactly.
Okay.
At a very high level, you can imagine this like a chain of signatures almost. So a validator has a public key, and then another validator appears in the next epoch, and this one signs this public key, and so on and so on. So we have that just with a lot of validators and 2 runs of signatures and more information in the middle. So yes, it is more complicated than we had before.
The problem is if we just do it like this, verifying this chain of signatures, basically it's linear, whereas the NIPOPOS were able to actually reduce it to something more logarithmic scale. And of course that's much better than having a linear verification.
Yes,
sure.
The linear...
Less data.
Yeah. The linear is going to be somewhere between, I guess, 2 and 20 megabytes a year, so still not a lot, but...
Per year, okay.
Exactly. But yeah, it's not nano-seeking.
Still every client would need to download and prove that
exactly
continuously. Okay, yeah,
which will if you are
not
just,
optimal.
Exactly. You are a fresh node, and Albatross has been running
You're a fresh
for,
node after 10 years, and you have to download.
200 megabytes and prove
start.
that and wait for
not very good for now
5,
nodes
10
in
minutes.
the browser. No.
Mhm.
So what we are using actually is what you call probably heavyweight cryptography, I guess.
Okay.
It's snarks, basically. It is not.
Right.
Yes.
Keyword alarm. Ding 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 ding.
Zero knowledge proofs.
Ah.
Yes. And yes, we are basically just using a snark that can just prove that all of these headers have that property. They are signed properly, and each one is ahead of the other, etc. All that we want to prove. But yes, it is somewhat a big.
And that would be then smaller. Would it also be logarithmic or
No constant actually.
constant?
Yes.
I like that.
Yeah.
It is.
I like that.
Yeah, snarks are really good because always constant, and it's always 200 bytes for anything that you want to prove. So either if you want to prove the smallest thing, like x equal y,
It's
or
200 bytes.
exactly if you want to prove the whole chain, it's always 200 bytes.
Okay.
You just get a lot more work out of it. But yes, so
Nice.
for the nano client, will also be very fast to download, very fast to prove because it's also constant. Well, to prove no, but to verify. To prove is actually linear.
Yeah.
Yeah. So yeah, that's what we are working on now.
Very cool.
Yeah, understanding
And that's
how we can do that snark.
I think that's very exciting to because that's actually you are on the forefront of that. The research, the state, right there, right? Like what's happening with snarks and how to integrate them into the proof of stake system and Albatross in particular, right? Yeah.
I mean, we can also talk a bit maybe about the challenges we faced there from a very basic initial idea of just using snarks as is,
It always starts with a
any
single
normal
idea.
snarks.
Simple idea, right? Just,
Yeah.
oh, we just use snarks.
I mean,
Done. But no.
No, it turned out to be way more complicated than that. I mean, I can talk about it, but it is quite technical. So.
Yeah, maybe just summarize it on a high level.
Okay, sure. So we are using the BLS signature scheme.
BLS.
Okay,
Yeah.
right.
I read it somewhere.
Yes.
At least for the validators, they are using the BLS signatures.
Yeah,
Yeah.
exactly. So that chain of signatures is all BLS, and that is the main thing that we want to prove, basically, is that these signatures exist and are correct. So we just thought, okay, we just pick a snark and just prove that, and all is fine. The problem is the BLS signatures exist in a given curve, an elliptic curve.
Yes.
Okay. The one that we are using now is the BLS 12381.
Okay.
Okay. So it has 381 bytes of size, hence the name, right? Simple. So most of the snarks library also are built on top of that exact curve, because it is a very useful curve. So where the problem comes from is if you have a snark on that curve, so the snark is on a curve of 381 bits, you can't actually prove statements about numbers that are of that size. You can only prove statements of numbers that are 255 bytes, I think. So if the signatures are actually 381 bytes, and the whole system they are trying to prove, then it is too large basically for what we want. Right. So what we need is another curve that can make statements about this curve.
That can handle. Oh, okay. So
exactly.
Yeah.
curveception.
Exactly. That is actually exactly what's happening here. Because normal snark you just make statements about numbers.
Okay.
So simple integers.
Yeah, basically every hash is a number in the end, right?
Exactly.
Yeah.
Okay. Yes. But the signatures are not numbers precisely; they are elliptic curve points.
Okay.
So I mean, in the end, treat them as numbers, but more specifically, they are points in.
Just take your word for it.
Okay.
But Pascal is nodding, so I think that's correct.
So yes, it's always good sign. But yes, so you need a curve that is larger than this curve in order to actually make statements about what is happening here. First, we started to research a bit into recursive snarks, there is a thing also, it's snark inception basically, where you can have various levels to infinity actually of snarks, each one proving
It snarks all the way down.
exactly. It is actually quite useful because you can, for example, if you have a bunch of snark proofs, I can create another proof that just
because
says
you said right, everything can be not compressed, but everything can be proven in a fixed
exactly
snark.
So if you
Fixed
can
length snark.
prove anything using snarks, you will think, okay, you can prove also that a snark proof exists for this,
I would think
and
so.
recursively.
Uh-huh.
So it turns out you can, actually, yes. Now, new problem about this. The current way that this is done is with two different curves, like curve cycles.
Okay.
So you can have 1 year and another year, and there's a very special type of curve cycles. That this one can make statements about this one, and this one can make statements about this one. So that's how you get this infinite.
Right, and then they are like one the other.
Exactly.
Alternating. They are alternating.
Yeah,
proofs,
they alternate.
basically.
So
Okay.
yes, at the very level, at the very bottom level, you make some statement about numbers on one curve, and then this curve can make a statement about what happened on this curve. Then this one can make a statement, and just keep going. Now, it is a bit unlucky that these curves are not very efficient.
Oh, right.
And
Okay.
exactly.
So
They are very special class of
it's
curves.
computationally intensive.
Exactly.
Okay.
And also, in terms of memory and everything, they're not ideal for this.
Okay.
And we also needed to have the BLS signatures on top of one of this, and it would be awful. It's to slow down a lot. Also, they're not really good libraries for it now, because it's really at the edge, I guess, of what's being done now in zero knowledge proofs. So another solution that we found, that is actually what we are doing now, is that instead of having this infinite recursion, you can just have one level recursion.
Okay.
Or finite recursion. So I can have one curve, and then I have a larger curve that proves this one, and is only used for that, and then I could have another, but each level you add a curve. They get progressively bigger.
So, so we're using a different curve for each step.
Exactly.
It's not recursive anymore.
You no longer have cycles.
Okay.
So you have like a chain of curves. So each level is going to add a curve to you.
And so it should end somewhere because it gets too big or not handleable anymore, or it's just it's not necessary anymore to go higher.
Because there's a chain at a given point. If you want 10 levels, you need 10 curves. So at a given point, you need to stop.
Okay.
You can't just recalculate 10 curves for infinity. And also, yes, they get quite larger and very difficult to handle. Okay. So you can probably make these two levels top, 3 maybe if you really want, but it's not something that you can do a lot. Thankfully, we only need one level recursion, because we have the signatures and we only want one level on top. Yeah. And that is it. So actually, yes, we are using, now we changed to another curve that we are using the VLS on, the VLS signatures. And then we are going to pick another larger curve to make proofs on that. Okay,
and do you already know which
it's going to be? Yes, the VLS one is going to be actually quite similar. It's going to be the VLS 12.377, because it is 377 bytes long.
Okay, 377, yeah.
Yes, mathematicians are not very creative with names.
Well, there are two hard things, right?
Yeah.
And naming things is one of them, so
yeah,
it's understandable.
And the other large one is called Short Weierstrass.
Short?
It's German.
Weierstrass.
Yes.
Weierstrass.
Weierstrass, that's a German name.
Short Weierstrass.
Short Weierstrass.
Yes. Yeah. My German is not.
My German is decent.
So in the next episode we might talk about the hard fork preparations and what we are planning to do afterwards.
Yes, yeah, that would be interesting, yes.
Like privacy. Or GXOs, maybe.
Yeah, these are basically two things that will come basically after the hard fork.
After Albatross is live.
Yeah, true. Okay.
Awesome.
But yeah, I liked it very much.
Yeah, thank you very much for this. This was actually really enlightening and very interesting for me.
Glad that everyone liked it.
And I'm happy that. Yeah. I mean, I think you also enjoyed.
Yeah.
I did like it. Also, when I start talking about math, most people just run. So
exactly.
Run so
it's hard to find an audience for this kind of topics, right? Yeah. So maybe we'll find some in our community. And with Richie. Hi, Richie.
Okay. So
Right,
then.
yeah.
Okay.
Thank you very much. And
Let us
Jin,
know. Also, let us know whether you liked it.
Yeah,
or
let us know
whether,
what,
yeah,
if this.
whether we should go into more depth about zero knowledge proofs, or whether we should talk more high level about stuff.
Yeah, and about
Yes.
more stuff.
And yeah,
instead.
just
Yeah.
comment, like, or whatever on any channel.
Comment, subscribe, and ring the bell. Right? Click the bell button.
Yeah, it depends on whether we're.
Oh yeah.
Are we putting it on YouTube? Maybe. Yeah, we are.
Yeah.
We are. Okay. Richie says
We
yes.
have enough footage.
Good. Perfect.
Okay.
But
Okay.
I think we're going to call it out of battery.
Right. Thank you
Okay.
very much for listening and
Thank you.
for viewing us. And until next time. Bye-bye.
Bye.
Bye.